Graphing a function rule is just where we take the functions and the patterns that we've looked at in the previous lessons and we look at the visual representation of those. So our target today is that I can graph equations that represent functions. So several things to think about when you're graphing, and these are things that you probably already realized from your previous experience of graphing. So the set of all solutions, so set meaning group, of all the solutions of an equation, they form the equation's graph. And remember what we've said about solutions, the values of the variables that make the equation true. So when you put those into that equation, they balance out. The graph may include solutions that are not in the table. That's why you'll see an arrow on graphs. This one does not have an arrow here, but it extends in the other direction. And we'll talk about why it does not extend below, but it does above. And thirdly, a real-world graph, meaning it's representing some sort of real-world application, it should only show the points that make sense in the given situation. So here's your example. You are paid $8 an hour to babysit. We've seen this example before. So here's our table. If you work for 0 hours, you get $0. 1 hour, 1 times 8 is 8. 2 hours, 2 times 8 is 16, and so forth. And so there are our coordinates. You can see that those are being graphed. Let's get a pen. 0, 0. Well, no, that's not it. Hang on. Okay, so if we were to graph these points, 0, 0 would be right here. 1, 8 would be like right there. 2, 16, just a little bit above the 15 mark. Okay, 3, 24, just shy of 25. 4, 32, so a little bit of, whoops, above 30 there. And 5, 40 right there. Okay, so you can see that those solutions fall on the line. And I'm only showing the positives of a coordinate plane. I'm only showing quadrant 1 because there's no negatives in this situation. You're not going to babysit negative hours. You're not going to be paid negative dollars. And so that's why it's only showing this portion of the graph. It is an endpoint right here because you cannot babysit less than 0 hours. So it does not extend infinitely the other way. It could extend infinitely the other way. Now I'm only showing up to, you know, I could show up like 8 hours or so, 6, 7, 8 hours, because typically you're not babysitting more than that amount of time. It could happen, that's why we have the arrow, but that's not the focus of the graph. Draw this thinker guy. No, I'm just kidding. But you do need to draw the words here because this is extremely important. When you hear the phrase make a graph, your brain thinks, like this guy who's thinking very deeply, I need to make a table. Don't try to graph it, just guessing where those points go. You have to have exact coordinates, and those coordinates come from the table, and then the table and its coordinates are going to come from the function rule. So if you were to graph a function from a rule, let's say we have this one, 4x plus 1 equals y. I'm going to pick some points, pick some x values because that's the independent variable. That's what you put in there. I'm going to multiply it by 4. I'm going to add 1, and that's going to give me the output, the y value, and that's going to build coordinates. Now when you're choosing coordinates, be easy on yourself. Don't choose negative 74.5 and positive, you know, 1/3 or something. Pick coordinates that are easy to work with. And you really need to have about 4 points for each time that you're graphing these. So for the first one, if I put 1 in there, put that in to x, 4 times 1 is 4. 4 plus 1 is 5. So I'm going to graph 1, 1, 2, 3, 4, 5 right there. Okay? And then if I have put 0 in there, 4 times 0 is 0. 0 plus 1 is 1. So 0, 1. Okay? And then decreasing some more and doing negative 1. I'm looking ahead and saying, well, if I put 2 in there, I'm going to go 9, which is going to be way up here, which is kind of off my graph. So I need to fill in the other side of my graph. So I'm going to choose smaller x values. So I put negative 1 in there. 4 times negative 1 is negative 4. Negative 4 plus 1 is negative 3. So negative 1 down 1, 2, 3. Okay. And then if I put 2 in there, we said 9, so that was 5, 6, 7, 8, 9. It's going to be kind of up here. And then if I put -2 in there, -2 times 4 is -8. -8 plus 1 is -7. So -2, 1, 2, 3, 4, 5, 6, 7. Uh-oh. I want that to be right there. Once you have all your dots plotted, you want to try and connect the dots. You can see that these fall in a line, which is very convenient. So I'm going to use a line to connect those. This function extends, so I'm going to put arrows on the end of it, like so. And just ignore the different colors. That's a black line going through there. There's no significance to the colors there. So you could have two different kinds of graphs. You could have a continuous or you could have a discrete graph. And so you can tell by just glancing at the pictures, a continuous graph is a line, it's connected. A discrete graph is dots that are not connected. So the continuous graph is unbroken, and it doesn't have to be a line. It could be even a curvy line like that, and it would still be considered a discrete graph. And I'm sorry, a continuous graph. And with a discrete graph and the dots don't have to fall in a line, they could go something like this, which would be the shape of a parabola, and the point is that they're not connected. Continuous is connected, discrete is not. The significance of this is when you're graphing real-life situations, you would use a discrete graph if the variables can only be whole numbers, and that is when you use a discrete graph. So if I were wanting to know how many, let's say, packages of batteries that I needed to buy, and the packages only came in packs of 4. Well, if I needed 20 batteries, then I would buy exactly 5 packages. But if I needed 22 batteries, I couldn't buy just 4, I would have to buy 5. So you have to ask yourself, do the variables that are being represented, can they be portions of a number, or can they only be whole numbers?